So in this lecture, we're going to look at how we can use the molecular orbital diagrams for pi systems to predict reactivity and understand reactivity. Understanding reactivity that involve just the rearrangement of pi bonds is really a phenomenal accomplishment of molecular orbital theory. So let's look at this. And this involves the idea of frontier molecular orbital theory. Did I spell it right? Yeah. Okay. Frontier molecular orbital theory. And in this theory, what we do is we say that most reactions occur by the in-phase overlap of the frontier orbitals of a chemical of reactants. Let's just write of reactants. Okay, so what this is saying is that if we have A plus B goes on to our product or products, what we're saying is that the frontier molecular orbitals of A and B are the ones that are interacting. And it's these interactions that encourage the formation of our products. Okay, well, what are the frontier molecular orbitals? Sorry, a few pages in here. Okay, so the frontier molecular orbitals are the molecular orbitals that exist at the occupied and unoccupied interface. The occupied and the unoccupied interface. It's actually a much simpler idea than at least these words can describe. So there are two types. There are the Homo and the Lumo. So we'll start with the Homo. The Homo is the highest occupied molecular orbital. It's the highest occupied molecular orbital, HOMO, Homo. So this is the highest energy orbital, and I should be careful, it's the highest energy molecular orbital. With electrons. And when I say with electrons, I'm saying that the orbital is occupied. Okay, so the orbital is occupied in this case, and it's the highest energy version of all of the orbitals that are occupied. So there could be many orbitals that are occupied, especially if we're combining sigma and pi systems, and this is the highest energy one that's occupied. Okay, so that's in contrast to the other frontier molecular orbital. That's the LUMO, which is the lowest unoccupied molecular orbital. Lowest unoccupied molecular orbital. This is saying that of all of the orbitals that we have, this is the lowest energy molecular orbital without electrons. And so if we're without electrons, were unoccupied. I guess vacant, LVMO, wasn't as catchy as LUMO. Okay. So what we're saying here is that according to frontier molecular orbital theory, reactions occur when the orbitals involved, when the frontier orbitals of two reactants interact. And that's specifically saying when the HOMO of one reactant interacts with the LUMO of another reactant. So if reactant A with a HOMO, reactant B as a LUMO, these things interact, that gives rise to the products. And it could flip where B has its highest occupied molecular orbital, the HOMO, and then A has the lowest unoccupied molecular orbital, that's the LUMO. Okay, so what we're saying is that most reactions involve the HOMO of one reactant interacting with the LUMO of another reactant. Okay, that's pretty cool. That's saying that when we have a reaction occur, it's all about the HOMO orbitals and the LUMO orbitals finding each other. Okay, so another way of looking at this is when we have nucleophile interact with a negative charge interacting with electrophile and a positive charge. The negative charge is attacking the positive charge, but it's really the HOMO of one thing attacking the LUMO of another thing. Now, why do I put the HOMO on the nucleophile? Well, the HOMO has electrons, and the LUMO is unoccupied. That means it doesn't have the electrons. So it's willing to kind of find things that do have the electrons. So a HOMO interacting with a HOMO, these things both have electrons. So it doesn't make too much sense to interact those two. But the HOMO and the LUMO, one with electrons, one without, those things can interact to form new molecular orbitals during the course of a reaction. So new molecules with new molecular orbitals. So we start with molecules and their molecular orbitals interacting with each other to make new molecular orbitals as we make a new molecule. Okay, so this is super handy with pi systems. So frontier molecular orbital theory is very helpful with pi systems. That is to say, understanding odd reactions like when you take a diene and react it with a dienophile to give a cyclohexene. Now we know this as the DA, or the Diels-Alder reaction. Well, it turns out that something else that I should mention before I tell you that it's the HOMO of the diene and the LUMO of the dienophile that give rise to the product is I want to also add that for a reaction to occur, the HOMO and LUMO must be similar in energies. Okay, they must be similar in energies. Okay, this is what dictates why the diene uses its highest occupied molecular orbital and the dienophile uses its lowest unoccupied molecular orbital. Okay, now I'm not going to draw this as well as I could to scale, but if we have the diene, here's our diene, we could consider its molecular orbital diagram as having 4 molecular orbitals. We did this last time. Gosh, I'm sorry. You're probably still writing that down. Okay, sorry, I'll go right here. I'm going to also draw the dienophile over here. So I'm going to scroll up a little bit. So I'm saying we're going to take the diene having its HOMO energy. Well, if we look, we've got pi 1, pi 2, pi 3, and pi 4. And I'm just going to, instead of considering the orbital shading for a moment, I'm just going to consider how these things are filled with electrons. Now, it turns out that when we have a diene interacting with a dienophile, it's the HOMO of the diene interacting with the LUMO of the dienophile. So I forgot I should put my 2 electrons in the dienophile. Well, let's find the HOMO and the LUMO for each of these systems. I'm going to start with the dienophile. So the HOMO is the highest occupied molecular orbital, highest energy orbital with electrons. That's going to be pi 1 for the alkene. The LUMO is then the lowest energy orbital without electrons. So there's just 2 orbitals. The lower energy one is always the HOMO. But now, for the diene, we actually have 2 orbitals that are unoccupied and 2 that are occupied. Well, the HOMO is the highest energy one that has electrons. And the LUMO is the lowest energy one without electrons, the lowest energy unoccupied molecular orbital. So I keep saying it's the HOMO of the diene interacting with the LUMO of the dienophile. So that's this orbital interacting with this orbital. These 2 orbitals interact with each other to form product. So the Diels-Alder reaction occurs by these 2 orbitals interacting. Okay. What we can do is we can actually take our picture from the Diels-Alder reaction and apply what we know about the shading for these 2 orbitals. So let's remind ourselves what pi 2 of butadiene looks like. If you go back in your notes, you'll recall that pi 2 has 1 node, and so that's where we split the orbital in half. So I've got 4 non-hybridized p orbitals, and their respective shading is going to show me what this molecular orbital looks like. If I have 1 node, that 1 node is going to strike right down the center, and we're going to have a system that looks like this. This is the HOMO, the highest occupied molecular orbital of butadiene. Now for an alkene, and we're also, I keep drawing psi, that's an old habit. If we consider pi 2, the second pi molecular orbital for our alkene, that's going to be a molecular orbital made up of 2 p orbitals, and we show the respective shading to once again give 1 node. The fact that they're both psi 2 or pi 2 and the fact that they both have 1 node is purely coincidence. I want you to pay attention to how the electrons fill these orbitals so that we can understand which is the HOMO and LUMO, because those are the things that interact. That's important. What's HOMO and what's LUMO is more important than how many nodes it has. Well, in these cases, they both have 1 node, sure. And that node number allows me to kind of get a baseline for how the shading is without doing a whole bunch of quantum mechanics. Okay, so it's these 2 orbitals that are overlapping when we do the Diels-Alder reaction. That means I need to correct my 3-dimensional stereochemical model from the Diels-Alder unit. If you recall, we did something like this. And we let, the diene come in from underneath to do some attack. But this actually has to match our in-phase interaction of our HOMO and our LUMO, because that's what frontier molecular orbitals say. We're going to use the most accessible electrons in the highest energy orbital that has electrons. That's the HOMO, and interact those with the lowest energy, most accessible empty orbital of the other reactant. That's another way of thinking about it. Okay, so HOMO and LUMO. So the way I had this was I went shading up, shading down, shading down. That allows me to have my one node and still match the shading from the HOMO. I'm just kind of redrawing it with a three-dimensional perspective. Now I'm going to take the LUMO and I want to match the shading. So I'm going to go dark on this side and light on top on the opposite side. That allows me to have in-phase overlap between these two lobes and in-phase overlap here. Now remember, you get to pick where you want the dark and light shading to start. So I could have started light up or dark up. Doesn't matter. Well, in this case, I just want to make sure that I find a way to orient these things so that we have in-phase overlap on both sides. Now, it's important to note that the in-phase overlap, gosh, I am getting too into this and now I'm writing sloppily. It's important to note that if I had used other orbitals, I would not get this in-phase shading to occur, this in-phase overlapping to occur. So it's due to kind of the symmetry of these molecular orbitals, the fact that we have this one node that we can get to this in-phase productive overlap across these interactions. And this is fundamental to what's called the Woodward Hoffman rules. Which, huge definition, huge unit. Suffice it to say, given the context, I'm going to say that pericyclic reactions occur by in-phase overlap of frontier molecular orbitals. Okay, so that's just a definition I'll throw out there because I feel like every organic chemistry professor in the country has to say the Woodward-Hoffman rule. Okay, we're going to look at some more reactions involving these frontier molecular orbitals to try to understand how some of these reactions of conjugated pi systems actually occur. Now, the thing to keep in mind is we need the phases to match up of our two reactants, but we also need the energies to match up. And the energies are a harder thing for us to grasp at this stage. If I backtrack in my notes just a second, I'm going to do that right now. I kind of hinted that the HOMO and the LUMO were close in energy. We can make them closer, even closer in energy by adding some substituents that raise the energy of the HOMO and lower the energy of the LUMO and the corresponding reactants to get better overlap of these two orbitals. And if there's better overlap, we're going to see a more efficient and faster reaction to occur. So it's not only about the phases, but it's also about the energy overlap. You may argue that, well, the HOMO, if you're quite astute, you could argue that the HOMO of the dienophile, the substrate on the right, reactant on the right, and the LUMO of the diene actually have an orbital match that works as well, so where you can get in-phase overlap. Now, it's just not often the case that you see the energies match up. Again, you can add substituents to then raise the energy on the diene HOMO and lower the energy on the dienophile, you can raise the energy on the dienophile HOMO, lower the energy on the diene LUMO to get those orbitals to have better overlap. And then you flip which orbitals are involved and you actually get different outcomes for reactions. For that to occur, you would add appropriate substituents and accomplish what's called an inverse electron demand Diels-Alder reaction, where you do a Diels-Alder reaction using the opposite frontier molecular orbitals, all substituent controlled because substituents can raise the relative HOMO and LUMO energy levels. When something's a good electrophile, it has a low energy LUMO. When something's a good nucleophile, it has electrons that are easily deposited by way of a higher energy HOMO. It's all about the HOMO-LUMO interactions to get chemistry to really work at all. I mean, it's just one theory that works really well. Okay, all right, so that'll do it for this lecture. We'll see you next time.